December 19th could decide whether 3I/ATLAS is a dying comet or something far stranger. November 9th, images show focused jets up to approximately 3 million kilometers, while spectroscopy and photometry imply mass loss near 50 billion tons per month. An energy gap scientists can't easily explain. Breakup, exotic ices, or directed thrust. Telescopes are ready. Let's dive right in. No one expected the night sky to change in November, but it did. And it began with a single image, one that made professional astronomers stop scrolling their data feeds and whisper to each other, "This shouldn't be possible." The object was 3I/ATLAS, a visitor not born of our sun, an interstellar wanderer that had drifted through the void for eons, until, this year, it brushed past our star and erupted with a violence that defied everything we thought we knew about comets. When the first enhanced frames came in on November 9th, 2025, the numbers looked wrong. Jets of gas and dust stretching up to 3 million kilometers, some pointed directly toward the sun, fighting against the solar wind itself. Others spread outward like glowing veins across the dark. It wasn't just beautiful, it was terrifying, because the math behind it didn't add up. To put it simply, comets run on sunlight. They warm up, ices vaporize, gases escape. It's a straightforward process until now. At one point, 8 astronomical units from Earth, Atlas, was releasing tens of billions of tons of material every month, an amount that simply cannot be powered by the sunlight it receives. Astrophysicist Avi Loeb from Harvard described it best. It's like watching a candle melt an iceberg. The energy deficit is massive. If Atlas were behaving like an ordinary comet, it would have to be 10 times larger than it appears through Hubble's lenses. But the images don't lie. The object is smaller, compact, and yet somehow producing energy on a planetary scale. So, what's fueling it? Some argue it's loaded with supervolatiles, rare ices like carbon dioxide and carbon monoxide that vaporize at lower temperatures. Others propose runaway reactions, where buried pockets of gas suddenly detonate as heat reaches deep layers. Yet, even with every creative explanation stacked together, the math still comes up short. Something is giving this object more energy than the sun provides, and that's when a chilling question started spreading through astronomy circles. What if those jets aren't natural at all? Normal comets form broad plumes, soft, chaotic, beautiful. 3I/ATLAS, however, shows precision. Multiple focused columns, some 1 million kilometers long, aimed in contradictory directions as if obeying a plan. How does a chunk of frozen rock fight against the sun? How does it produce thrust in perfect opposition to radiation pressure, maintaining straight, consistent streams? To do that, material would need to be expelled at tens of kilometers per second, velocities typical of rocket exhaust, not sublimating ice. At that speed, each jet would generate measurable thrust, enough to alter the comet's path slightly, an effect already hinted at in recent astrometric data. This pattern is what keeps scientists awake at night. If those jets are natural, they're rewriting physics. If they're not, there's something far more unsettling: controlled propulsion. Everything now revolves around December 19th, 2025. That's when Atlas will reach its closest approach to Earth, about 270 million kilometers away, too far to hit us, but close enough for every major telescope on the planet to lock on. And that's when we'll find out which story we're living in. If Atlas appears as a cloud of fragments, a diffuse mass spreading apart, it means it broke apart naturally after its near-sun pass on October 29th. A dramatic death, yes, but a comprehensible one. Nature gone wild. But if it remains whole, if the jets are still firing, if its nucleus looks stable and organized, that's when the questions get harder. Because then we're forced to ask, is it surviving against the laws of physics, or operating under another set of them? Avi Loeb's team ran the equations again, using data from spectroscopy and photometry. The results were unsettlingly consistent. Mass loss, approximately 50 billion tons per month size, far too small to sustain it naturally. Energy, exceeding solar input by a factor of 5 to 10. It's the same pattern that once surrounded Oumuamua, the first interstellar visitor detected in 2017. Another object that mysteriously accelerated away from the sun without any visible jets. Back then, Loeb proposed it might be a light sail, an engineered craft reflecting sunlight for propulsion. The idea made headlines, critics laughed, and yet, here we are again, facing the same question with better data and a brighter target. When you put the pieces side by side, the pattern is too familiar to ignore. Oumuamua behaved strangely, Borisov behaved normally, Atlas behaves impossibly. So maybe, just maybe, we're not looking at a coincidence. Maybe we're looking at a sequence. If Atlas broke apart during its near-Sun encounter, we should now see multiple fragments scattering along its orbital path. Each fragment would shine independently, spinning, venting gas erratically. The brightness curve would fluctuate wildly. But if it didn't, if a single compact nucleus remains, still venting powerful jets weeks after peak solar heating, that would mean it's tapping into an energy source of its own, chemical, nuclear, or something beyond our comprehension. In that case, December 19th wouldn't just be an observation day, it would be a turning point for science itself. Because if Atlas is still whole, still accelerating, still behaving with precision, then we might have to accept the unthinkable. It's not just a comet, it's a machine. Let's break down why that idea refuses to die. For a comet to produce thrust against the solar wind, its gas must exit at enormous speed. Ordinary sublimation produces around 400 meters per second. The Atlas jets, they appear to reach tens of kilometers per second. That's rocket exhaust velocity. If you replace ice with engineered propellant, something that ignites or reacts internally, the math suddenly balances. The massive energy gap closes. Momentum matches, trajectory changes make sense. It doesn't prove artificiality, but it makes it possible. And when physics allows something extraordinary, you can't just look away. Spectral data deepens the mystery. Unlike most comets, Atlas isn't rich in water. It's 87% carbon dioxide with traces of carbon monoxide, materials that belong in the frozen outskirts of alien solar systems, not the warm regions near stars. That means it formed in extreme cold, possibly beyond any planet's orbit. Yet, after millions of years drifting through interstellar radiation, it still retains volatile ices intact, almost as if it was protected. Some astronomers theorize a carbon-rich crust may have shielded the interior, like a thermal shell. But that same crust appears to vent in organized, symmetrical jets, suggesting structure, not random cracking. Natural materials don't behave this way, unless, of course, the crust isn't natural. Could it be a protective hull, a thermal barrier designed to regulate energy release? That's the kind of question that makes scientists uneasy, because it's both absurd and mathematically consistent. The truth is, astronomy isn't allergic to mystery, it thrives on it. But the discipline also fears sensationalism. For every groundbreaking discovery, there's a dozen false alarms and misread data points. Yet, 3I/ATLAS refuses to fit any comfortable box. Too bright for a dying comet, too symmetrical for chaos, too powerful for sunlight. And the closer we look, the stranger it gets. Even if we strip away the alien narrative, we're left with a puzzle that challenges the fundamentals of cometary physics. Where does that extra energy come from? How can a small, icy body eject millions of tons of material for weeks without tearing itself apart? If it's natural, it's redefining what natural means. If it's not, then we're witnessing the first interstellar technology ever detected by humankind. Every major observatory, from the James Webb Space Telescope to ALMA in Chile, has scheduled time to watch Atlas on that day. Spectroscopy, photometry, thermal mapping, every instrument will be aimed at the same point in space. What they see will decide everything. If the nucleus has fractured, scientists will celebrate. Another extreme but natural phenomenon, finally explained. But if it remains coherent, stable, and active, the paradigm shifts, because it means that something out there can survive what destroys everything else, and that survival demands an answer. Beyond the excitement lies real concern. If Atlas has fragmented, the debris field could spread across millions of kilometers, posing a long-term hazard to satellites and space missions. If it hasn't, its sustained activity might reveal an entirely new class of interstellar objects, resilient, powered, and intentional. Either way, December 19th is more than a date on a calendar. It's the moment humanity faces a cosmic mirror, one that could show us our limits or our reflection staring back from the stars. Because maybe, just maybe, Atlas isn't here by chance. Maybe it's here on schedule. December 19th isn't just another date. It's the day we find out if 3I/ATLAS is a dying comet or proof that something far more advanced is passing through our solar system. Whatever the answer, it will reshape how we see the universe and our place in it. If you believe discoveries like this matter, help us keep exploring the truth. Like this video, leave a comment with your thoughts on 3I/ATLAS and subscribe to Galactic Breaking News with notifications turned on so you won't miss what happens next. Together, let's stay informed, stay curious, and keep looking up.